that turned on in just a second. From current slide. Okay. Don't know of any new announcements. Think I'm back on regular schedule with office hours, but things are still crazy. Monday and Wednesday, Whatever
happened to the truck? Did you get a new one?
Yeah. We already got it.
What'd you get?
Honda CRV. Yeah.
What year?
This year. It's new.
2018?
Yeah. Well, it's either 17 or 18.
You want to get another RAV4?
Nice.
What's that?
You didn't want to get another RAV4?
No, well, it was more expensive. And
No, I mean, you got to have a little quality.
yeah. We went.
Got you a 4-wheeler,
And the other thing is, we were surprised. The cargo space was just a little bit larger in CRV, and we wanted that too. So, and it may be just the local dealers weren't giving us as good as the one. The one we got less expensive was up in Jasper, and they have. What's that?
Did you get a Scott from Toyota used?
No, it was Honda of Jasper.
Oh, okay.
Yeah.
Oh, you said you got a new. Never mind.
Yeah. All right. Okay. So, office hours tomorrow, 7:45 to 11:45, Birmingham campus. As far as I know, we should be there. I should be there. And then Monday and Wednesday, I think I'm back to 3:15 to 5:15. Monday and Wednesday here on this campus. Tuesday and Thursday right before this class, 1:15 to 3:15. Today was sort of messed up because I had to advise some students during my lunch hour, and then that threw my lunch hour later, and then everything got a little messed up. But somewhere in that time frame, that will usually be my office hours. Okay. Now, let me say this. The first person turned in a research paper.
Yeah.
You have just barely a month to go, a little bit more than a month to go. Please don't forget the research paper.
How much is that? How much of your grade is that paper? I don't remember.
How much what?
How much of your grade is that paper?
It's a test score, and it can't be dropped. Okay? Your lowest test can be dropped, but not the paper and not the final.
All right.
Okay. Say again? Okay. What's that? The instructions are on Blackboard in two places. Under content, you'll see like the second or third thing down will say research paper instructions. Also, if you go to first day of class on the YouTube videos, that will say syllabus. And when you go to syllabus, you'll see the research paper instructions will be following the syllabus. So I think that was all on the first day of class. So you'll get me hear me talk about it on the YouTube video. You can just read it statically on the under content, under research paper instructions. I'll never finish reading words. Oh, research paper topic. Okay, good deal. Excellent, thank you.
Oh wait, they turned in their topic or their whole paper?
I got the whole paper in from one. A few people have turned in topics.
Oh.
Okay.
When is the topic due by?
The second week of the term.
Okay.
Which was about a month ago.
Okay.
But no. Anytime you can get it to me.
Okay.
Okay. All right. Any other questions before we get going on today? So let's talk a little bit about today. We're going to go for about 2 hours of Chapter 3, Energy. If we get far enough in it, which I think we will, we'll have time for the lab, which will be the next 2 hours. And then it won't take you 2 hours unless you really dawdle on it. And then the last 30 minutes will be the test. Okay? That's the test on Chapter 2. And you can have formula and equation sheet. And if you remember, I said early in the term, only the first test had that many calculations to fill in the blank. This test and all subsequent tests before the final, the chapter test, will be mostly multiple choice. A lot like those conceptual questions in the back, but not the same ones, of course. But they'll be covering the same material pretty much. A few, maybe one or two per chapter, maybe a few chapters, 2 or 3 or 4, that would be calculations. And then maybe 1 or 2 fill in the blank, answer a question. But most of them are going to be multiple choice. And you can have your formula and equation sheet. If you haven't gotten that put together, I'd say get it together before the last 30 minutes today. Okay, any questions? All right, where we left off last time, we were talking about the fundamental law in energy is the conservation of energy. Energy cannot be created, nor can it be destroyed. Energy is energy. It's there. It can change forms like crazy. You might say, but wait a minute. The process of internal combustion, you know, the spark plugs and all that kind of stuff, that releases the energy of the in the car, which makes it move. Well, no, the energy was originally stored in the
Gasoline.
Yeah, the gasoline. It was stored there because many millennia ago, little green leaves captured the sunlight and converted that into carbohydrates first, and then over time became hydrocarbons, which ultimately we then burn. So, no, energy is not created nor destroyed. So, now I think we talked about most of these. Work, motion, position, radiation, light, that's where a lot of our original energy came from. Heat, chemical energy, the petroleum, the green plants, the food you ate, stored chemical energy. Nuclear energy, the energy of that's stored within the nucleus of an atom. That's atomic energy, the other way to talk about it. Mass itself is a form of energy. Seems strange, huh? But I bet you all of you know the formula that converts it.
Yeah.
What?
E equals MC squared.
E is equal to MC squared. Some little known scientist was once famous for coming up with that one. Who's that?
Albert Einstein.
You got it. Okay? So E is equal to MC squared. Now here's just an illustration of this. M is, of course, the mass. Now, seldom do these things do in terms of kilograms, but let's just take 1 kilogram. Okay? You'll never, well, on the sun this is happening, but on Earth, hopefully you'll never have a kilogram of mass being converted to energy at one time. Okay? What is C?
Speed of light.
Speed of light. Anyone know what magnitude that is?
It should be on the front cover of a book.
Yes, you got it. Speed of light. It sure should be here. Speed of light, yeah. Next to the last one under physical constants.
Okay.
3.00 times 10 to the 8 meters per second. Of course, you're going to square that, and what would that give you?
I don't know.
Square 3?
Oh, 9.
9. And what happens when you square 10 to the 8?
10 to the 10th?
No,
No.
10 to the 16th. You double it.
That's
Okay? So you have 9 times 10 to the 16th meters squared per second squared. 9 times 10 to the 16th, that's 90, 000, 000, 000, 000, you know, 5 sets of 3s plus the 0 after the 9. That's how big that becomes. 1 kilogram times that, we give you how many joules of energy? Enormous amount of energy released from a very small amount of mass. And that's why atomic explosions are so deadly or release so much energy. Okay? So, that is your mass itself. Now, as far as I know, I've never heard of anyone converting energy back to mass. I don't know if that's possible, but no mass can be converted to energy. Okay, sources. Okay? We've already talked about petroleum. Another one that's been in the news a lot lately is coal, kind of on its way out, no matter what certain people say. Moving water. How do we use that energy? Hydroelectric dams, of course. Other ways too, hydroelectric dams. Nuclear energy, nuclear power plants. All you're doing there is splitting the atom, releasing enormous amounts of energy, and then using that energy to boil water, make superheated steam, and the steam is what turns the turbines into make the electricity. Solar, that's directly solar cells. The other way solar is used, influences wind to a certain extent, and so anything, they don't even list wind turbines, but that would be moving air, would be as well as moving water. Now, what are the uses? Well, petroleum, we think of transportation, but also generation of electricity. Natural gas is used for that a lot. Coal has been used for that a lot. The moving water generation of electricity. Certainly petroleum or coal has been used for heating. Electrical is used for heating, which came from moving water or the others. Cooling, of course, that's kind of the reverse process. And lighting, of course. So lots of different uses for those various forms of energy. And energy changes its forms just incredibly smoothly, okay? And it's hard to keep up with what's what. So let's first look at work, okay? One definition of work is the product of an applied force and a parallel distance through which the force acts, okay? I apply a force to the chair, and the chair moves a certain distance, okay? Now, after it left my hand, I'm not doing any work on it. But while I'm applying the force, that time there, the force I applied times the distance before I released it, or it moved on off, that is work. Product of applied force and the parallel distance. Now, I'm applying a force here. Is it moving? No, just because you apply a force doesn't mean you're doing work, believe it or not, okay? Now, if I apply a force here, in this direction, am I doing work? Some, but it's not this times that distance, because it has to be parallel. Force is what kind of quantity? Vector quantity, meaning the direction matters. You can break this vector down into a perpendicular component and a parallel component. Only the parallel component to the actual movement does work on the chair. The perpendicular component does absolutely no work on the chair. Not a bit. Okay? Okay, I guess that's enough on that. The formula for it would then be work is equal to force times the displacement, okay? Or distance, if you want to call it distance. But it has to be in the same direction, okay? So, this guy lifting the box, okay? His force is upward, the box lifts upward. He's doing work on the box. I'm doing work on the book. I'm lifting it upward, the force is up, the displacement is upward, okay? That is force times displacement. I'm doing work on the box, on the book, okay? Force times displacement. What are the units in the U.S. customary? Unit for force?
Pound feet.
Pound. And distance, displacement? So actually we usually call it foot pounds, okay? Now, some of you probably have used a wrench before that's calibrated in foot pounds. Was that a work wrench?
Torque wrench.
Torque wrench. Was torque the same as work?
Yes.
No. Work is a scalar quantity because a force times the displacement, those are both vectors, that is called a dot product if they're in the same direction. Torque is a force times a force, and that's, say again? Turning or twisting force, and that's because the forces are perpendicular to each other. You are exerting the force on the torque wrench this way, your displacement from the thing that you're twisting is that way. Those are perpendicular to each other. That is a vector quantity. Torque is a vector. Okay? I know you've seen this. When someone rev an engine, and you've been looking in the hood, what does that engine? Yeah, the engine is trying. If it weren't for the motor mounts, it'd be flying out of the car, literally. Okay, so the motor mounts are what's holding it in place because torque is a vector quantity. It's force times the displacement, but it's a perpendicular force. That's a vector that's called a cross product. That's not the same as work. Measured in the same units, but it's not the same. It's a vector. This is a scalar. Okay. Now in the and we call it foot-pounds so stick. Okay. In the SI units, what is your unit for force? Newton. And displacement? Meter. A Newton meter is a
Joule.
Joule, exactly. Now, they spell Newtons with a small letter. They spell pounds with a small letter. The abbreviations with a small letter. Feet is a small letter. Abbreviation is a small letter. Newton's a small letter, but its abbreviation is?
Capital N.
Capital Y.
It's a name.
Named after Sir Isaac. Okay. Meters, small letter. Not named after anyone. It's a Latin word or a French word for to measure. Metro. Okay. Meters and measurement. Joule, however, they didn't give the unit for it. Does anyone know what it is?
Capital J.
Yes.
Capital J.
Capital J. Why capital?
Probably named after somebody.
Yes. James Prescott. James Prescott Joule.
Oh, okay.
Okay, yeah. James Prescott Joule.
James Prescott.
a pretty interesting character in himself. He was the son of a brewer, okay? I think he brewed probably beer, maybe whiskey, I don't know. He was a brewer. However, James Prescott Joule, the son, was a sickly child, and he couldn't really participate that much in the business. There are many thoughts that he may have had hemophilia. Anyone know what that means?
Blood.
Yes.
Blood.
Yes.
When your blood has trouble clotting.
Exactly.
Oh.
It's a platelet problem. You don't have enough platelets, so if you get a scratch, you may bleed to death because it doesn't ever stop bleeding. They have to do all sorts of things. So he had to take it very carefully when he was young. So therefore, basically, he studied a lot and didn't do that much physical work because he couldn't do that much physical work, and he was a brilliant mind. But back then in England, people in what you would call trades were not usually very well educated necessarily, just enough to do their trade. But because he studied so much on his own and probably had tutors too, his father made a lot of money, he was very well educated and became quite a famous scientist, except that usually tradesmen weren't allowed into the scientific circles. Those were reserved for the elite people, you know, the lords and they weren't usually all that smart. There were a few exceptions, of course. But he was taken under the wing by a guy named William Thomson, who was actually Lord Kelvin, who was a brilliant scientist, and he introduced Joule into the Royal Academy of Science in Britain, and so much of his work did get published. And fortunately, William Thomson did that for him. Okay? Pretty interesting character himself, James Prescott Joule. All right. There should be, I guess, another slide here, but I sure don't see it. So let's move on to the next one. The units of work and energy in the SI system is Joule. What is it in the U.S. customary?
Foot-pounds.
Foot-pounds. Very good. Now, zero distance, zero work. Okay? In fact, I'm holding this book here. Where's my force? Upward. If I move it this way, am I doing any work on the book? No, because it's perpendicular to the force I'm applying. Okay? I'm not doing any work on the book. Now, you would probably get a great deal of argument from someone, but if you, I hate to ask this question because to this crowd anyway, have you seen things like the cheerleading competitions? Okay? And when they have those pyramids that they're holding, usually a lightweight gal at the very top, and there may be 3 or 4 layers there, and the big sturdy guys are at the bottom, and they're holding her there, are they doing any work?
Yes.
No. They did work getting her there,
Okay.
but while they're holding her, tell them they're not doing any work. They're sweating bullets, but they aren't doing any work. Getting her up there, yes, that required work. Holding her there does not, because there's no displacement. No distance, no work. A little personal example. When we first moved into the house where we currently live, we had been looking at it, and my wife really liked it. The only thing is the previous owners, or some previous owner, had built an extension. It's an old 1930s Tudor-style house. We liked the style, everything about it. It was built sort of on the hillside, but they had a flat part here. The yard came down in back, went down in front, but it was on sort of a level area. Nicely built stuff. But some previous owner had wanted to put a den on the back of the house. Well, that went into the hillside, okay, because the hill was coming down like that. And so when we looked at it, the house looked squatty then, because the den, you just had very narrow windows, and they were right above the soil level because it was built to the hillside. And it kind of looked like it was sort of squatting there, okay? Front looked really nice, the sides looked nice, the back was a little bit bizarre, and they didn't really finish it as nicely as the front and sides were. But it was there. I really didn't care as much for the looks. The looks weren't all that great. But what I was concerned with, here you had water going downhill against the back of the house. That is going to create some hydraulic pressure, okay? And in time, that could weaken the back part of the house. But not only that, you had the windowsills, the soil, basically almost in contact. Soil to wood contact in the southeast, not good. Termites, okay?
Yep.
Now, of course, it was a fairly recent addition, 10, 15 years prior, so I'm sure they used treated lumber, so therefore that would resist termites for so many years. But over time, the treatment would leach out of the wood and the termites would feast, okay? So for 2 reasons, I told Karen, I said, if we get this house, we need to do something to get the water to move away from the house and also to get the soil well below the wood line. Okay? She said, well, good. I wanted a patio anyway. Not exactly my idea of what we were going to be doing. Unfortunately, I planted the idea, so here we came. That year was the first year I taught here at back then we were Western State Technical College, and it happened to be my first year here. In the summer, enrollment was down, and I was a new kid on the block, and because of other reasons, I was a full-time temporary, not full-time permanent yet. I was going to be made that, but in the process of getting that. But so when they didn't have enough classes, the senior math people, and there wasn't any science person but me, but they got priority as far as getting a full load. Well, I was teaching the automotive program at the time, their math classes. Actually, back then, they had their own math class. It was math for automotive. I can't remember its number now, but they had their own math class, okay? And they were on a system like y'all are, a co-op system, but we were in 10-week quarters rather than 18-week terms, semesters. So they came to school 5 weeks and were home for 5 weeks. I mean, at the dealerships for 5 weeks. And the first year they did it like y'all, and then the second year they flipped over and yeah, just like you do it now. Like say they did every term. Now y'all do 8 and 8, 8 and 8, and then full. Everybody was in school in the summer, 10 weeks. Okay, but they did 5 weeks on and 5 weeks off. Well, I was teaching the first year students their math, so they were here the first 5 weeks. I had 2 classes of them, and then they were gone the next 5 weeks. So I was here part-time in the summer. I had teaching either 2 or 3 days a week. I think it was 2. So I was home 3 days a week, and then the last 5 weeks home all the time. That's when I started my project of digging out the patio. Okay? And I had a pick, a shovel, and a wheelbarrow. Okay? And digging out the patio. And if you've done any digging anywhere in this area, you don't have to go far before you hit
Clay.
yeah, clay was all over the place.
Oh.
But you hit rocks.
Oh.
Okay? And they're sitting right in the middle of where, okay, I did the one smart move. Not all that smart, but better than the average for me. My wife had taken a hose and lined out where she wanted the patio to be. And she wanted it curvy, that was more aesthetic and stuff like that. And I had it way back there. So I said, well, dear, can't you help me some? And she would help me when she came home. After a while, she pulled the hose in. Okay. Reduce the size of the patio a little bit. Okay. But anyway, just about the center of the patio, I'd been going at it for a while, and suddenly I hit, and it was below the soil line. I mean, in the deepest part, I would be about, the soil line came up to about here. It fell off toward the house, but in the deepest part, it was pretty high. I hit this rock. And it took me quite a while to establish the boundaries of the rock because it was big. It was big around. It was very tall compared to where I was going to put the patio, the bottom of it. And I worked at that thing, digging around it. Probably took a couple or 3 days, hauling off the soil and everything. But then, trying to get it out of there, I had cheater bars, I had iron pipe, I had whatever I could, trying every way I could to pry that loose. And I was grunting and sweating. It was summertime, and speaking ill, and various things, and I couldn't budge that rock. And no matter how much I sweated and how much I grunted, how much work was I doing? 0. You tell me that day, you might get a rock inside your nose. Okay. But that's absolutely, in physics sense, 0 distance is 0 work. Okay? So here's an example. You have a book down on the second shelf from the bottom, and you lift it and put it up on the top shelf. Have you done work on the book?
Yes.
Yes. The force was upward. The displacement was upward. Force times displacement is the work you did on the book. And these books, by the way, are approximately 1 kilogram of mass. Okay? Multiplied by what to get force?
Distance.
No, that's to get you work.
Oh.
What gives you force? This is mass with kilogram.
Time?
Okay? Not velocity.
Weight?
I got this written down.
You better. Well, you're going to be using it. To get weight, what do you do to mass?
Gravity.
Acceleration due to gravity.
Acceleration. Okay, acceleration due to gravity. That's G. So 1 kilogram times, what is it in the SI
MG.
unit? Say again?
9.8.
9.8
Units
units.
per second. No.
Meters per second squared. Acceleration. That gives you force. That would be about 9.8 newtons, right? That was the force I have to use to lift the book, and lifting it, what would that be? 1.5 meters? Then 9.8 times 1.5, that would give you how many joules of work you did. Force and displacement are vectors. Work is a scalar quantity. Okay? Because that's what they call a dot product. Okay? Because vectors can multiply either by dot product or cross product. Cross product produces a vector, that's torque, and work is a dot product producing a scalar. Okay, seems like there should be another slide here, but there's not. Before we get to simple machines, let's go on and do examples 3.1 and 3.2. This will give us room to do it. How much work is needed to lift a 5.0 kilogram backpack? What's that a measure of? Mass of the backpack, okay? To a shelf 1 meter above the floor. What's the 1 meter? That's 1.0 meter.
Distance or displacement.
Okay, that's your distance or displacement, D, that you're going to lift that backpack. So how much work is needed to lift it? What is work?
Distance over, no, distance.
Okay, distance is in there. Force times the distance. And what's your force here?
5. No.
5 is mass.
Yeah.
1 what? No, 1 is distance. Second? 1 meter is your distance. How? What?
Mass times accelerator.
Ah, very good. The force is your weight. The weight of that backpack, which is mass times the acceleration due to gravity. So that would be, this is force. What is your mass?
1 meter, or 1.
No, that's your distance.
5 kilograms.
5.0 kilograms, mass. What's your acceleration of gravity in the SI units?
9.8
9.8. What units?
meters per second squared.
Meters per second squared. Multiply those out. I think that comes out 44.0. Someone got a calculator? Check me on that. I think it's right. 49. Actually 49, isn't it? Yeah. 49.0. What units? Kilogram, meter per second squared. That has a name. Newton. Very good. Then you multiply that force, 49.0 newtons, times 1 meter. And what do you get? Pretty easy multiplication there. A little louder. 49.0, or you don't need the 0.0. Newton meters, but Newton meter is also called a joule. Okay? Now, if we went back to our fundamental units, that would be kilogram meter per second squared times meter would be kilogram meter squared per second squared. That's the fundamental unit for a joule. Kilogram meter squared per second squared, that's a joule. Kilogram meter per second, that's a newton. Newtons are vector quantities, joules are scalar quantities. Okay. Yep, they got 49 joules, good for them. Okay. Let's clear that off the screen. Everybody got it?
Yes.
Okay. Let's do how much work is required to lift a 50-pound box. What's 50 pounds a measure of?
Mass.
Really? Say again?
Weight.
That is weight. And weight is also force. Weight and force are this, weight is a type of force, okay? So that's your weight or force, okay? Vertically a distance of 2 feet. What's that? They just said it. Distance. So how much work is required? And by the way, weight is little w, work is capital W.
Okay.
What's the formula for work?
Force times displacement.
Force times the displacement or distance, and that would be
50 tons.
50 pounds times 2 feet, and that would give you not that hard of math.
100 foot-pounds.
100, what you said, foot-pounds, absolutely. All right, and Chelsea's here. Has anyone else come in since I called roll? Haven't really been watching that carefully, so. Okay, I know you're in here. There you are. All right. All right, any questions? Notice the difference here. Kilograms measures mass. You have to get that into force units. Pounds measures force or weight. That is a force unit. You don't have anything that you need to convert or change that. Okay? So 100 foot-pounds. Good deal. All right. Now, the next slide is on simple machines. Okay? Now, that's in the book. You have to turn a page from where we just were, and that would be the sort of bluish kind of blurb at the top, say 2/3 of that 2-page spread there. This is your thing on simple machines. And you deal with these all the time. The basic premise on your simple machines are work in equals work out. That's not work out like, no, that's different. But in reality, it never is. Okay? We'll just leave that alone now. We'll assume that the work input is going to equal the work out. Okay? The reason I say not, you always have some energy loss. If you count that in the workout, then work in is equal to work out. Okay? This may not be useful work. The force is multiplied by the ratio of distances. Can you lift a car?
No.
All right. That's interesting.
Not personally.
Oh, what do you mean by that?
You have to use a lift or a jack
And how does that work?
by doing the work for you.
No, you do the work. But think about this.
Multiply the word.
Say again?
They
Oh, okay.
multiply the word,
Okay.
or they-
Think of this now. When you're doing a jack, you got it under wherever you're trying to lift, and you push down with a certain force over a distance. You're doing work. Okay? Now what does the car do?
Go up.
How much?
Fraction.
Just a little bit. So the work in equals work out. Except you went a huge distance, a fairly large distance, and exerted a certain amount of force. It pushes up a larger force, but a much smaller distance. But work in equals work out. Work in is force you applied times the distance over which you applied. Work out was the force the car came up times its displacement. So that's the key here. Force in times distance in equals force out times distance out. Most of the time in that jack, small force in, big distance in. Big force out, small distance out. So yes, you can lift a car. Okay? And you've probably done it many a times, okay?
Multiple times a day.
Yes, okay? And that's you. Now, if you got a machine lifting it, then that's something else. But even those hydraulic jacks, which are really nice, you're doing the force over a big distance and the car is coming up. Big car, but coming up a little distance. So that's what, so when they talk about the multiply by the ratio of distances, what you do is divide the work in by the distance out, and that ratio of distance, DI to DO, which is usually large, right? Big distance in, small distance out, that's your force multiplier. So your force that you inserted in, which maybe 100 pounds, 150 pounds of force, it comes out much bigger force because of that ratio of distances. And that's what this is. The force out, the reverse sides of it, is the ratio of distance in to distance out of times force in. That's why we call this the multiplier. Okay? In many contexts, we'll call that the mechanical advantage. Okay? And that's how you're able to lift a car, even though you can't do it directly as you said or something like that. Okay? Now, what are some examples of these simple machines that take advantage of that? Has anyone ever tried to split wood?
Yeah.
Okay? You take your fingers and dig it and pull it apart, right?
Mm-hmm.
Yeah, you do, right. Okay.
All the time.
All the time, okay? Now, what do you typically use?
Wedge.
A wedge, okay? And you come down with a huge force okay, for you, but you're trying to wedge this into the wood this way, a distance there, but it's pushing the wood out a very small distance this way, but that's how you split the wood. So a wedge, okay, I'm sorry, I missed the inclined plane.
That'd be a ramp.
Yes, exactly. I was trying to think of an example of you. I bet you have lifted an engine onto a thing by putting on a ramp and rolled it up, right? Guess what? You've applied all the work if you did that, but you went up the ramp. You went a long distance this way. Your vertical distance wasn't that great, but you force times the distance this way equal force times the distance that way. So you lifted a much bigger engine than you could have done by just lifting, okay, because of that ratio. And a wedge is really two ramps together like this. That's all it is. A screw is like that, which is holds stronger. Screws or nails?
Screw.
Oh, for sure. And one of the reasons why, actually what a screw is, if you think about it, is an inclined plane wrapped around an axis. So that's what you're doing when you're using, and that's what's one of the things I was doing, was trying to get some batteries in some old stopwatches so we could do the lab today, and I was tightening those screws. Okay? A lever. We're pretty familiar with that too, right? That jack, that was a lever. Okay? And generally with a lever, you have a fulcrum that you put somewhere, usually close to the load, and your jack's here. You call it a cheater bar, right? Okay? And the longer this distance is compared to that distance, that gives you your mechanical advantage. It's actually the distance you pump it and the distance it lifts, but it's proportional to those lengths. A wheel and axle. Okay? Use that on cars all the time, right? Your engine is turning the axle, but then you've got a big old wheel at the end of it, so that gives you more distance traveled, a bit less force. The force on the axle has to be pretty great, okay? But that's another kind of simple machine. Pulleys, come-alongs, other names I can't think of right now, but the very simplest one, just a single pulley at the top, and you pull down like this. What's your mechanical advantage?
1-to-1.
1-to-1. No mechanical advantage really. All you're doing is changing direction. You pull it down this way, the weight lifts up that way. That's all that's doing for it. But if it goes around the top, comes down and goes back up again, you pull here, what do you have? 2-to-1. Why? Because you pull twice as far, because say you pull this much length of the rope here, right? Well, half of that comes from here, this side, and half from that side. So basically the load is lifted only half as far. So you have a 2-to-1. You can lift twice as much with one trip around the bottom on a all I can think of is come along. That kind of a pulley. If you have 2 wraps around the bottom, 4 times. Okay? So the ones around the top, they just change direction. The number of turns around the bottom, that gives you your mechanical advantage there. I think I've asked this question several times. I'll probably keep asking it. Have any of you ever been to the McLean Science Center downtown Birmingham?
Yes.
Okay? Have you seen that device over there? You can sit in the chair and pull on the pulley and lift yourself, or not. Okay? It used to be there. It was there for several years. We used to take various people there when they come into town, kids, nieces, nephews, that kind of stuff. And that was a pretty interesting thing, because the more turns at the bottom, the easier it was to lift yourself. If it's just that one turn at the top, had to be a pretty strong kid or person to be able to lift himself like that. Get one turn around the bottom, much easier. 2 turns around the bottom, almost a piece of cake. Of course, you have to do a lot of pulling to lift yourself just a little bit. That shouldn't have an advantage. Okay. Here is the example of the lever. This gal lift 300 pounds? Look like she can?
Probably not. Yeah.
Doesn't look like it, but sure she can if her lever is long enough. Actually, we've talked about Archimedes before, right? Have I mentioned him?
Yes.
Okay. Archimedes actually had a fairly famous quote. He said, "Give me a rock to prop it on and a long enough lever, and I can move the world." Okay? In reality, he was actually true, but you don't have that set up you could, but he could. If it was a long enough mechanical advantage here, and he's pushing down far enough, he could lift. Because that's exactly what she's doing. Pushing down with only 60 pounds of force, but going over 2.5 feet, that's the effort distance, okay? Then she's lifting 60 times 2.5 is what? 60 times 2.5. 60 times 2.
150.
And half of 60.
150.
Okay, that's 150. That'd be 30, so that'd be 150 foot-pounds of work. And 300 pounds she would lift how far?
No.
Say again?
2 feet.
Not 2 feet, half a foot. 150 would be half of 300, so she lifts at half a foot. 2.45 feet down, she lifts a half a feet, but she still lifted 300 pounds. Good for her. If you put the fulcrum here, okay? This is called the resistive force of the load force, load distance, effort distance, effort force. Okay. Fits into the formula very nicely. Okay. Now, there is a blurb at the top of that page 87, a figure there, 3 different types of levers. Okay? And one of these types is your first class lever, which is what she has here. Okay? The fulcrum's here. As long as the resistive distance is shorter than the load distance, she has a positive, greater than 1 mechanical advantage, or force multiplier. If you move this back here, not nearly as great. Okay? If it's right in the middle, all you have is a seesaw, right? Okay. And speaking of seesaws, did you ever play on the, or teeter-totter? Some people, that's mostly northern, I think, calls it that. But I was always the heaviest kid in the class in elementary age. And so I always had to sit way short, and the lighter people had to be on the longer end of it, or else we couldn't play. I just sat there and they sat up in the air. Okay? So not very much fun. Okay. So anyway, that's what they call a class 1, first class lever. The second class lever is when you have the fulcrum at the end and the effort on this end, and so the fulcrum's down here, and you put the load somewhere in between here. Now, what's that? That's the second class lever. What's an example of that?
Wheelbarrow.
A wheelbarrow, exactly. Your fulcrum's down there. You're doing the handle here. You can lift a heavier weight. You lift twice as much, or 3 times. Depends on how far back you are. The amount there, that your lever is there. And that would be a wheelbarrow. The third class lever has the fulcrum at the end, and you have the load at this end, and your effort is in the middle. What's that an example of? Say again?
I said, oh boy.
Yeah. But you've used them.
Haven't.
I did when I was digging my patio. A shovel, exactly. The fulcrum's down there. Okay, I'm sorry. The load's down there. The fulcrum's here. I'm lifting here. All I'm doing, I'm lifting. I can lift a lot more than a spadeful of soil, right? That's not that much, but I'm throwing it a longer distance. Same thing with pitchfork when you're throwing hay or something like that. You're trying to get the distance out of it. That's the third class lever. Not much of a mechanical advantage there. There your ratio is less than 1. But you're trying to get more distance and speed out of the load, not necessarily lifting a larger load. Okay, now let's turn back in the book to page 65, left-hand column, power. That's what we're going to deal with next. Okay? Let's start with distance or displacement. Remember, back in chapter 2, we started there. And then what do we do with that distance or displacement? Divided by time. The time rate of change of distance is distance divided by time. We did it in lab. Velocity or speed, exactly. Okay? And then once we got speed down, guess what we did? You did it in the second lab.
Acceleration.
Yes, divided by time again. The time rate of change of velocity is acceleration. And then the last time I think we were in here, we talked about the time rate of change of momentum.
Inertia.
Okay, no, inertia is related to mass. That's force. That's not how we define force, but that's, I think, how Newton defined force, was the time rate of change of momentum. So whenever we get a good quantity that seems to do a lot of good things for us, well, let's measure the time rate of change of that, and we may get something new. Well, the rate at which work is done, time rate of change of doing work, is called power. Exactly. Or the rate at which energy is transformed. That's power. Now here's one horse pulling with 550 pounds of force, lifting a block, and a 550 pound block, 1 foot, in 1 second. Guess what that is?
The horsepower.
1 horsepower, you got it. 550 foot, that's a foot pounds per second. That's horsepower. Foot pounds measures the work he's doing. Force times displacement, that's the work. Per unit time, that's power. Force per unit time is power. Here's the formula for it. P is equal to work. Capital W is work, little w is weight. Weight divided by time. Pretty exciting, huh?
Oh, yeah.
Oh, yeah. Okay. So that's what power is. Now let's go back to me digging the patio. My digging the patio. Okay? I worked probably pretty solidly for most of about 5 weeks. Those 5 weeks of the second mini term in the summer that summer, digging the patio. I had other things to do the first times when I was home just a couple days a week. But those 5 weeks I was pretty much digging there. And unfortunately, with that big rock in the middle and other things, I only got about half of the patio dug in those 5 weeks. And it was time to come back. In fact, it was Labor Day weekend. Yes?
What I do when you come to dig rocks, you just build a fire on that rock till it's flaming hot, and then you douse it with water, and usually it'll explode.
Would that work?
I think it's basic chemistry.
Okay.
But anyway,
It was a hot, dry summer, and I think the city of Birmingham would have probably frowned on me igniting big fires on that size rock. Okay, so I probably wouldn't have gotten by with
How
that.
big was this rock?
It was,
compared to this room,
yeah, it was at least this tall. Okay, and at least this big around. It was oddly shaped, but approximately that. It was massive.
At least a ton.
It was. It seemed more, but yeah, at least that. Okay. So, in 5 weeks, I moved half a patio's worth of soil. Okay, and then it was time for the term to start. I was going to be working 5 days a week. Didn't know it at the time. Let's see, now I guess I'd already taken my classes. Anyway, I was going to be full-time at work, not having that kind of time to work, and then days were shorter, not going to be able to work that much. So we decided that Labor Day weekend, before I was going to come back to work the next Tuesday, let's go on and, You might be asking yourself, why didn't you just hire a bobcat to come in and dig it out anyway? Well, number one, I'm cheap, but worse than that, there was no room for a bobcat to work because we have trees, the house, it was really cramped. So by the time I got half the patio dug, now I had enough open space here that you could get a bobcat in there. So we called the bobcat, a guy that did bobcat work, and he came out, and in one afternoon he dug the rest of the patio. I had done half of it in 5 weeks. He did the other half in half a day. What was the difference? Who did more work?
He did. You did.
No, you did the same work. I did half the patio, he did half the patio. What was the difference there? Time. And therefore power. Power is work divided by time. And believe me, the bobcat he had was a lot more horses than me, okay? At my best, on an average day, I was probably a third of a horsepower or less, okay? That bobcat had to have been 200 horses or more, okay? So yes, he had much more power. We did the same work, but he was much less time, so therefore the power was much greater. I did the same amount of work, a great deal larger time, my power was much less. Make sense? Yes. Okay. All right. Now, what are the units for power in the SI system? What would work be measured in? SI system. Joules. Okay. Time? Seconds. What's a joule per second? Anyone know?
That would be a watt.
A what?
A watt.
A what? A watt. Right. You got it. Okay. All right. A watt. Okay. Named after James Prescott Watt. Now here's the sad news. Work's parameter, the symbol we use to represent work is capital W. The unit for power is capital W. So don't get them confused. This is the unit, always has a number in front of it. 15 watts, 150 watts, 3,000 watts, something like that. Work is just a symbol that stands for work. So that doesn't usually have a number in front of it. So don't get those confused. In the U.S. customary system, horsepower, okay? Which is, again, U.S. customary, remember weird conversions, 550 foot-pounds per second, okay? Strange unit. Work, foot-pounds per second.
How did they come up with that?
Here's what, it's interesting, good that you asked. Go back here, a guy named James Watt, the guy that they named the unit, SI unit for, he came up with the idea, he said the average dray horse, which was the big work horses, that they had back at the time, the average that he could do in a day's worth of work in a day, he considered 1 horsepower. And then you broke that down into seconds, and that would be, it came out 550. So it's weird. Yeah. So that's what he said, the average dray horse, what it could do in a day. And so that was per day, and then you broke it down into seconds, and you got foot-pounds, 550 foot-pounds per second. I can't handle that. Okay, nowhere close to that. On short term, maybe. Okay, but on the whole day, nowhere close. Okay. 550 foot-pounds per second. Not a bad thing to write down and bring with you on the next test. Okay? All right. So, James Watt named the horsepower. He identified that unit, and then later they named the SI unit after him because he had done some of the early work in power. Now, the lab we'll be doing today, you're going to be walking upstairs, timing it, measuring how far, and oh yeah, all right, extra, okay. What a benefit this class is, okay? Yes. Okay. Yes. I'm sorry. You mean now or
Well, I have to be working 5:30.
at 5:30? Okay. Well, by 5 o'clock, if you're not already taking the test, tell me and I'll let you go and start it. So wait, you have to be at work or you have to leave here at 5:30?
I have to be working at 5:30, but it's like I can leave it about 5:20 to get done.
Okay, well, tell me 30 minutes before you have to leave. And if we're not already through the lab, you can stop and take your time.
Okay.
Yeah.
Can we take a break right now?
Yes, we can. Yeah, yeah. If you want to take a break, let's take a break and we'll get back to this. Boy, if I ever get all this grading caught up, it's going to be a miracle. Okay. We are recording now. Any questions so far? Okay. Here it comes back on. So power is the rate at which work is done. The units of the SI system are watts, and the US customary horsepower. Very good. Okay? And the lab we do today is walking versus running upstairs. We'll talk about that as it gets closer to time. Okay? Now, one thing I've noticed, and it's not a surprise because lots of things, everyday uses of words means one thing. Physics, the definition has to be very much more precise. And the word power we misuse like crazy. Okay? When we mean energy, we say power. For instance, what bill do you pay for your lights and that kind of stuff every month? The power bill. Are you really paying for power? No. What are you paying for? The energy that you use. Have you ever noticed the units on that power bill? What you're actually paying? What are you paying for? Kilowatt hours. Okay. Kilowatt, watt measures power, multiply power by time, hours, and guess what you got? Kilowatt hours. But let's think back. If power is work per unit time, if you multiply both sides by time, kilowatt hours, then you're paying for work or energy. That's what you're paying for. You're not paying for power. Power is the rate at which you use energy. You're paying for the amount of energy you use. Okay? So the power bill is really an energy bill. Okay? Probably a good definition would just call it an electric bill. Okay, that would do it. Now, actually, my grandmother, many years ago, used to always call it the light bill. Now, why do you reckon she called it that? Because when they first installed electric lights, that's all the electric energy. She still was using her wood stove. She still was using the furnace that was probably what is that?
Coal or?
No, it was actually the liquid.
Kerosene.
Well, probably not kerosene. Huh? Propane. I think her furnace ran on propane. They had a tank outside and they come and fill up the tank. So no, all she used the electricity for was the lights. So it was a light bill for her. You know, over time then, they started using more and more things. But today we can hardly get by without it. But back then it was called the light bill. Now we call it the power bill. Both of them are wrong. It's the energy bill is what we're doing. All right, here is the example. And this will be us today. This is Melba walking up the stairs. And then, no, I'm just kidding. All right. So this old guy, not Melba, this old guy just creeping up the stairs here. Guess how much work he's doing? His mass times that vertical distance. Horizontal distance is no work because that's not against gravity. It's how much he's being lifted. So the amount that he walked up times his weight, that would be the energy that he's expending. Now this whippersnapper here, going up pretty quickly, doing more work or less work?
Doing
The same work, because if he's got the same mass, the same weight, then he's going the same distance, the work is the same. The difference is the time. This one's going much longer time to do the same work, so therefore lower power output. This one's going much shorter time to do the same work, much greater power output. Okay? So the distance, the time is the key here. The longer, just like the Bobcat, did half a day what I did in 5 weeks. Okay? Much more power behind the Bobcat. Way much more power behind the Bobcat. Okay. Make sense? And that's today's lab. We're going to be doing something very, very similar to that.
One time.
Huh?
Just one time.
You got to walk it, you got to run it. Okay. But there'll probably be pretty close to 3 people per team. You only have to record 2. I suggest that you do all 3, but the page is only set up for 2, but you got plenty of room to put a 3rd one in. So if you want to talk your way out of it and be just a timer, you can do that. But you have to go at least half a flight to do that. So we'll show that later. Okay? Now, there is a thing here called bookwork. You can think through that if you'd like to. I think we've done just about everything else here. Read the book. We don't have time to go through everything. Let's do the last 2 examples here, and these are example 3.3 and 3.4. They're not the last 2, the ones on power. An electric lift can raise a 500 kilogram mass. So it's a 500.0 kilogram, and they already told you what it was, mass. Okay? A distance of 10 meters. They already told you what that was. 10 meters is your distance. Okay? In 5.0 seconds. What's that a measure of? That's your time. Okay? The question is, what is the power of that lift? How do we get power? What's the formula for power? Work power is equal to work divided by time. Do we know the work? Do we know the work?
We know the distance.
We know the distance. Got it.
So
Okay.
with the distance we can get the work.
What's that?
With the distance we can figure out the work, correct?
No, with whatever else we got.
Force. We got to figure out.
We got to figure out the force. What is the force involved here? Another term for force, another type of force is weight. What is the weight you're dealing with here?
500 kilograms. No.
Nope, that's a mass. So what is weight? Boy, this is one formula you ought to know, especially before today's test.
Acceleration of gravity.
Yes, it's mg. Weight, or the force due to gravity, is mg, always. Okay? And what's your mass?
500 kilograms.
500 kilograms. And what's the g?
9.8 meters per second.
9.8 meters per second squared, since we're dealing with SI units. That's per second squared. Acceleration due to gravity, mass times acceleration is a force. Anyone know what that is? I think it's around 4,500. No, 4,400, I believe. No, 4,900. I can't add. 4,900. What units? Force measured in? It's force measured in newtons. Okay. All right, so there's your force. That still doesn't give you your work. What's the work? force times the distance. So the work, W, that we're looking for here is force times the distance. As long as they're in the same direction, and these are. So that's 490 newtons times, what's your distance? Say again? 10.0 meters. And what's that as a 10 times 490? 4,900, what unit? Joules divided by how many? 5.0 seconds. Okay? And that will give you, 5 will go into 49, that will go 9 times, 5 will go into 40, that'd be 8. I think 980 joules per second, which is what?
Watt.
What?
Watt.
Yeah, watt. Okay. That's 980.
Got me.
Okay. 980 watts. Or, if you wanted to do a smaller number in a bigger unit, that would be
98 kilowatts.
0.98.
0.98.
3. Kilo is 1,000, so you move it 3 places. So that would be 0.980 kilowatts. Sorry. All right. Okay. No, it isn't.
No.
This is. I think I dropped the unit somewhere.
Oh,
It's 9,800. Let's see. It's 9,800. Somewhere we dropped. Oh, yeah. 10 times 500, that'd be 4,900
oh, okay.
newtons. And that would be 49,000 joules. And that would be 9,800 joules per second, which would be 9,800 watts, which would be
98 kilowatts.
9.8, right?
Yeah, 9.8 kilowatts.
Okay, 9.8 kilowatts. All right, 9.8 kilowatts. What would that be in horsepower? Okay, we may not have talked about that yet. So let's go back and find that. I think, therefore I am. Oh yeah, on page 66, the bottom part of the page there, we were told that a joule per second is a watt. A watt is a very small amount of power. A kilowatt, a much bigger amount of power. Megawatt, a huge amount of power. And it takes, and here's the key, 746 watts to equal 1 horsepower. So they gave us that there, 746 watts equals 1 horsepower. Now that is a conversion, okay?
You said 746?
746 watts is 1 horsepower. So go back here to where you had 9,800 watts, okay? That was how much energy you had, 9,800 watts. Multiply that by, okay, let your units lead you. You're trying to get the horsepower. You got a conversion, okay? Always let the units, put your units in their place. What unit goes where? This blank is for numbers, that's for units. Always put the units in their place. What units do you put where there? One goes on top, one goes on bottom. One's above the line, one below the line. What goes where? Put the units. If you're trying to get from watts to horsepower, you're going to need those 2 units on either side of that line. Which one goes where?
The units on the bottom that cancel out?
Yeah, you want the one on the bottom here to cancel with that, so therefore you put watts down there. Okay? That's exactly what you do. So that leaves horsepower for the top, right?
Yes.
And what's our, now match the numbers with the units. How many horsepower per watt or how many watts per horsepower? It's right there.
746 watts per horsepower.
746 watts is 1 horsepower. There's your conversion. Okay? Now, when you have it set up this way, notice your watts cancel out, and that leaves you with, you multiply the numerators, divide by the denominators. So the 9,800 divided by 746. What would that give you? If anyone's got a calculator?
13.1.
13.1. Is that right?
That's what I got on my calculator.
Try it again. 9,800 divided by 746. Yeah, 13. Yeah, okay, you got it. I'm sorry, I was misreading. They rounded just to 13.
Oh, okay.
And the reason they did, I don't know why particularly, I guess because back here, the seconds only had 2 significant digits, so therefore you can't get more than 2 significant digits out. So about 13 horsepower. Okay? Everybody see that one? All right. Let's clear the screen, unless there's any questions. Yes. I'm sorry? You'll need it now? Okay. Find it. Oh, I think I may have it back here. Oh, wait, I'm in the wrong step. No, I thought I had one here. No. All right, here he is. It's in the wrong place. Okay. You want to go next door to do it? One of the offices or the class? Let's see if anyone's in there.
I don't know. Swing length is triggered.
One. Oh, you hit that button.
All right. All right. Example 9.4 says a 150-pound person
3.4?
is 3.4. Example
You
3.4.
said 9.4.
Oh, I'm sorry. A 150-pound person. What's that a measure of?
Mass. Weight.
Weight, which is a
Force.
force. Okay. All right. Weight, which is a force. Runs up a 15-foot stairwell. What's that? What's that a measure of? Distance. Very good. Okay. In 10 seconds. What's that a measure of? Of course, that's time. Okay. What is the horsepower rating of that person? So what are we going to have to do first? I'm going to go back to what power is. Not weight divided by time. Work divided by time. Power is equal to work, capital W, little w is weight, divided by time. Okay? But what is work?
A force.
Okay, it's not a force. It has to do with forces. What is the formula for work?
Force times distance.
Force times the distance. Do we know a force?
Yes.
What is it?
150 pounds.
150 pounds. Okay. Distance?
15 feet.
15 feet. Okay. Multiply those out. I think it's 2250. Is that right?
Uh, 50 times 15. Yeah, 2250.
Okay, so that'd be 2250 what units?
Foot-pounds.
Foot-pounds. Okay, divided by your time, which was 10 seconds. And that gives you not that hard.
225.
225 what units?
Horsepower.
At
No.
foot-pounds per second. There they are, right there, foot-pounds per second. Now what we have to do is convert that to horsepower. Does anyone remember what that conversion is? We had it on a slide a while back.
1 horsepower equals
Say again? That's 746 watts. We're not dealing with watts. This is back a few slides before that. Remember our good old, say again, the horse slide.
550 pounds.
550 foot-pounds per second. Okay? All right. So that would be 1 horsepower is 550 foot-pounds per second. Okay? So what are we going to have to multiply this by? Blank blank equal blank horsepower. What unit goes where?
You're trying to get the horsepower.
Yeah,
You want to cancel out foot-pounds per second.
right.
So foot-pounds per second goes on the bottom.
On the bottom. Foot-pounds per second goes below the line, and horsepower goes above the line. So everything here cancels out. And what? How many horsepower per foot-pounds per second? How many foot-pounds per second per horsepower? It's right up there. Say again? There it is. Say again?
1 over 5.
Yeah, 1 horsepower is 550 foot-pounds per second. Match the numbers with the units. So you multiply numerators, which is 225 times 1, divide by the denominators. 225 divided by 550. What's that? Anyone got a calculator?
225 divided by 550
Yeah,
is 0.409.
0.41, let's call it. Okay, because it looks like we had 2 significant digits everywhere, and that's what they got. 0.41 horsepower. Okay? We will be doing something very similar to that in lab today. All right? Any questions on calculating power in any of its ramifications? Okay. So, we're moving now to 3.2. Motion, position, and energy. Okay? This is a kind of weird title for this. Motion represents one form of energy. We call that kinetic energy. Position represents another kind. We call that potential energy. So energy is both of those, okay? And more, okay? So first, work and energy are related. If you do work on a system, you're adding energy to the system. If the system's doing work for you, you're getting work out of the system. The system is losing energy. So they are related. Here is the definitions we use. Energy is the ability to do work, and work is the process of changing an energy level. Now that energy level may be potential energy level, it may be kinetic energy level, but it's the process of changing an object's energy level. It could be something else even. Okay? Those little green leaves out there are changing the energy level of the chemicals in those, increasing their energy of carbon dioxide and water, making a highly energetic sugar fructose, sucrose, whatever. Okay. So work is the process of changing energy level. So what we'll be doing is studying the relationship between work and energy associated with position. So we're going to start with the position first. The energy associated with position. Anyone know what that's called? And then we'll do the relationship between work and the energy of motion. Anyone know what that one's called? Okay, we'll run into it. Okay? Energy associated with position is your potential energy. Okay? Now, there are many kinds of potential energy. I lift the book, I've changed the energy level of the book. It's now up here. It has more energy than it did when it was down here. Don't believe me? Stick out a foot and I'll drop it. Okay? You can tell there's more energy when I hold it higher. That's called gravitational potential energy. We're increasing the energy due to gravitational pull. Okay? There's other kinds of potential energy. I already mentioned chemical potential energy stored in the leaves or in petroleum or in coal or in various things like that. You have spring potential energy. We'll be talking about that a little bit later. Any kind of energy that is an energy related to position, that's a potential energy. We're going to deal with gravitational potential energy. I like to call this GPE. The book just says PE. There's several kinds of PE, so I like to call it GPE. One of the major things we deal with is measuring the height. How high have I lifted the book? 1 meter? 2 meters maybe? Okay? Half a meter, whatever. How high have I lifted? So the change of H. Now I like to call it delta H because that's what you're really doing. Because you're measuring from some level, we call that the reference height. Now if I'm lifting the book from the desktop may be the reference level. But if I were lifting it from the floor, same height here, we have a different reference level. If I lifted it compared to the ground outside, that's yet a different reference level. So you always have to establish what is your reference level. If you're calling this the level above sea level, then you would use whatever it is down in Gulf Shores or Mobile Bay or somewhere, what sea level is. So you have to reference your height. And generally we'll call that the zero reference level. What is the lowest height the book can go in this particular problem? If it can only go to the desktop, use the desktop as a zero reference. If it can go to the floor, use that as a zero reference. If it goes to the ground, use the ground as the reference level. And you measure your height from that zero potential level, zero reference level. We also have elastic or spring potential energy, electrical potential energy, chemical potential energy. There's tons of different potential energies. Okay? Not measured in tons, by the way. Okay. Work can change the potential energy. The potential energy of the book is whatever it is now. I do work on it, I increase the potential energy. I release it, it decreases its potential energy as it falls. It does work on the system. So work can change the potential energy of the object. If I have a spring here, and it's at its equilibrium level, if I stretch it, then I am increasing its potential energy. If I compress it, I'm increasing its potential energy. It's only at zero potential energy when it's at its equilibrium position. Okay? Kinetic energy can change into potential energy. Okay? World Series got over yesterday, right? Houston Astros beat the LA Dodgers, right? I don't know who the pitchers were or anything, but I bet you some of them threw pretty fast. I think that one reliever for LA was supposed to be a real fireballer, right? I don't know for sure. That catcher back there, what was his job? To stop it. In other words, to change that kinetic energy of the ball into potential energy. Now, I bet you after the game, his hand might have been a little sore, maybe bruised, Okay, anyone ever caught many? Yeah, you know that it could be quite a bit of work that you're having to do back there to change that. Changing that kinetic energy into potential energy. When those batters swung the bat and the ball went way up in the air, they just changed the kinetic energy of the ball to potential energy, gravitational potential energy. At some point it stops and falls back down, changing that gravitational potential energy back to kinetic energy because the ball gets faster and faster as it comes down. Always happens. Potential energy, either due to work or due to kinetic energy, can be changing. All right. Here we have, not a good idea, but someone was on the 4th story of this building. We don't have 4 stories on the building, but they decide to hold the book out. Okay? Now, if you're holding it just above the floor of that 4th story, that could be your reference level, and then the 0 potential energy level would be there. This would just be mgh, if that was your H. However, if you're holding it out over the street level down here, not a good idea, then potential energy would be, if you use this as a 0 reference level, this would be the H. Okay? However, if you kept the reference level there, but held it out the window, 0 is there, so your potential energy can be negative. Okay? Now this H is not the same as that, and I don't like the fact that they use this. This would be this H here, whatever that is. Looks like maybe, I don't like that they use the same thing. What they're trying to illustrate, potential energy can be positive if you're above the reference level. It can be negative if you're below the reference level. But these are not the same H's, so they should name that something else. These or something else, so you won't think it's the same one. Okay? All right. I believe that we have a couple of problems or examples with potential energy, but I believe also we don't have time for them. Isn't it 5:15?
Yes.
Okay, that's time for us to start the lab. So we will start the next class on Tuesday with example 3.5, bottom of page 69, and we'll go from there. Okay, now we're going to hang here in the room. We're not going to a lab today. We're going all over the building, okay, because we're going to stairwells. So just hang tight with me here. Let me put this on pause, and I'll explain to you what you'll be doing in your stairwell. The whole group will go to one stairwell, the closest one, okay? Then we'll split up, and I'll take the rest of you to other stairwells, but I'm going to explain to you what you're going to be doing in each one. I'm going to explain as much as I can here while it's more comfortable. Y'all are sitting, and, you know, I've got it all. Okay. You probably need a lab, don't you? You want one of the teams that have... You got one? Okay. Okay. Okay, did everybody get a copy of the lab? I didn't know I passed out that many, but... Okay, he has a copy. Is that right? I did 3 3 3s. He wasn't counted in the threes. Everybody else got a copy?
Yeah.
Okay, you got one? Okay.
Somehow you passed out one extra.
Okay. All right, so what we're going to do is go down to the stairwell. I'm going to tell you how we're going to go about measuring the height that you're going to be walking and then later running. I'm going to explain to you where the timer will be and how you do the timing. Now, some of you with the older stopwatches, these are sometimes can be a pain in the neck, so hopefully they'll work okay for you. They've been abused by students for many years now. Okay. Now, here's what I'm going to say later, but I want to say it now while you're all listening. Okay? When it says walk up the stairs, do that just very leisurely. A nice walk. Okay? The one with the stopwatch is going to be on a landing, and he or she will see right when you start and right when you stop. And by the way, the button for starting and stopping is around 1 to 2 o'clock, and the one for reset is around 10 to 11 o'clock. Okay? Don't touch the middle button. It changes the mode. It's all set up right now for you. Start, stop, when you record it, reset. Okay? Unfortunately, some of those older stopwatches, they don't always stop like they're supposed to, and they don't always start like they're supposed to, so be careful with them. Okay? Now, after you do the timing of that same person will then run up the stairs. Now, run is in quotes here. Does that mean go as fast as is humanly possible?
Yes.
No. Okay? I don't want anybody tripping, breaking noses, damaging stairwells, any of that kind of stuff. All right. Getting them bloody, okay? So, when I say run up the thing, just do faster than a walk. You can run as fast as you safely can run with no accidents. I want 0 incident reports today, okay?
Can we double step?
You can do however you want to, walking and running. I just don't want anyone falling. So run safely up the stairs. All you have to do is make sure you're faster than a walk, okay? And if you are trying to really break speed records, be sure you do it safely. I don't want to have anyone falling down the stairs.
First.
Yeah. So, does everybody understand that? Okay? Then I'm going to unplug my computer, and I'm going to take one with me. If someone else shows up, I'm going to have to come back and get, I guess I'll take more copies.
Chris can do anything out there.
Well, David's in that group too.
That's what they like down for.
Yeah, you're up.
All right. Let's go to the closest stairwell. Those who have meter sticks, bring them. Every team should have a stopwatch. Bring it. If you want to leave the box for them up here, you can. But if you take the box, be sure you keep up with the box. Okay. Everybody get into the stairwell here so you can hear and see. Everybody in the stairwell here so you can hear and see. Okay? Everybody in? Okay, come on, everybody in the stairwell here.
Come into the lab.
What's that?
Come into the lab.
Yeah. All right. Is everybody in?
You got one more.
One more. Okay. Yeah. Okay. Now I'm going to set my.
You may hold it.
That's all right. I think I'm loud enough to do. Okay. First thing you're going to do, if you'll look, hopefully you've read the lab, and we're going to do slight depth change for the procedure, but not too much. You're going to be filling out the data sheet on the back. Okay? The first thing it asks for is the height that you're going to be moving. So what you're going to do on these stairwells, you're going from this level to the level above us there.
So 2 flights.
Okay? It's not 2 flights, it's 1 flight, two stages. Okay? Now, notice it's asking for, the first thing, your weight in pounds. Okay? So hopefully, you ladies, if you don't want to tell the truth, you don't have to. Just use whatever weight you want to. You guys, there's no reason you should be a little more aggressive. Yeah, right. Okay. Is that kilograms? No, I'm just okay. All right. Now, the next thing it asks for, and by the way, if you're volunteer A, then it's the same weight for both walking and running, right? If you're volunteer B, you're saying, now, if the third person, or even the fourth person wants to do this thing too, then the third person can be over in the right-hand margin, the fourth person the left, or wherever, if you're going to get all of them in there, okay? So, the next thing it asks for is the vertical height of the steps in feet. Now, what it says to do is to measure the height of this step in inches, multiply by the number of steps, and then that gives you your height. Well, number one, I'm not certain they're all the same height, and besides, that's such a pain in the neck to do. Here's how I recommend that you do it, if you will hold this for me, okay? Now, we're measuring in feet, right?
Yes.
So don't use the meter stick as if it's 3 feet. It's not. 3 feet is 36 inches. So go from the floor here, 36 inches, make a mark here, go up another, that's 3 more feet, that would be 6 feet, and somewhere here, so right there, I'm going to go across here, assuming that's level, okay, and then go up another 3 feet, and then someone's going to get up here, and we're not measuring, you can't see it from where you are, some of you can,